Greetings once again from Rescue Shuttle Control. You're doing a great job. We have now determined that you are successfully acquiring analog data with your hero and responding to it with actions controlled by logic in the hero. That's exactly where we want to be in order to be able to successfully control the recharging of your batteries and get your shuttle up and running. So we're ready to take a big step today. We're going to build on your success from our last communication, and we're going to now add some more sophisticated logic and some more sophisticated control on top of what you've already accomplished. As we look at our work from our last session, we will not be changing the analog or the digital circuits at all here. We'll keep our same photoresistor circuit that we had before, and we'll concentrate today almost exclusively on modifying our hero code. And the purpose of this, what we're trying to achieve today, is the ability to monitor and respond to the state of charge of our batteries, to be able to have the hero monitor that state in real time and report that information back to us over the serial monitor and take appropriate actions. So that's our goal for today. And since we won't really be changing the circuit any, we should basically focus our attention on our code and see what kinds of new concepts and changes will be necessary in order to accomplish our goals today. Let's start off by looking, as we often do, at the upper part of our code block where global variables are defined. You will recognize this code that we used last time that defines these integer variable values for example, the sensor pin, the onboard LED, and so on. And we have our usual setup and loop routines. In the loop routine is the place where we were reading the analog sensor pin and then writing information out to the serial monitor. Well, we were writing to the serial monitor and we were also flashing the onboard LED in response to that. Today we'll focus mostly on the serial monitor and not do too much with the onboard LED since we've pretty much mastered that, and our focus today will be on sending data. So we have some new things that we're going to add today and introduce you to. We're going to introduce some new variables. Now these variables are different in that they're not integers. You'll recall that an integer is a counting number. It has no fractional part. It's just 1, 2, 3, etc., or negative integers as well. In mathematics, an integer can have any value up to infinity or negative infinity. When we represent an integer on a computer, we're constrained because we are basically representing that integer by a finite number of bits. So for example, if you only had 2 bits, 2 binary digits, you could represent the number 0 with 0, 0, the number 1 with 0, 1, the number 2 with 1, 0, or the number 3 with 1, 1. So you could represent 4 different numbers with 2 bits, 0 up to 3. Similarly, if you had 3 bits, you could represent all the numbers from 0 up to 7. Last time we saw that we were basically getting numbers from 0 up to 1023. That would correspond to 10 bits because 2 to the 10th power is 1024. Now, as it turns out, an integer, an int here in our code, can represent numbers up to about 32,000. Plus or minus 32,000. If we wanted to represent a number bigger than 32,000, say 50,000, we'd need an additional bit. We can do that in this code by using a special kind of variable, and that is an unsigned integer. In an unsigned integer, we take the bit that's usually used to say whether the number is positive or negative and use that to add extra range. So we could go up to 64,000 with an unsigned integer. So that's what we're going to do here. So I'm going to add to our list of variables an unsigned integer named battery capacity, and we'll set it to 50,000. So in some units, we are going to say that our battery will be full when it's reached 50,000, and we represent that with an unsigned integer. We have some other variables here, an unsigned integer, which is the battery level. So we'll be watching battery level as it rises until it hopefully approaches 50,000 when the battery will be fully charged. We're also going to be keeping track of time as it goes by. And since we've been measuring time in milliseconds, it could be a pretty large number. So we'll represent time with the variable ticks here, which is also an unsigned integer starting at 0. Finally, we'll have an unsigned integer, which is just the value 100 milliseconds. And we're going to use that to change the amount of time that we wait before we do interrogations of the circuit. The reason for defining it here and not in the code is that if I wanted to change it to 200 milliseconds, I could change it in this one location and not have to go and find every place in the code where it needed to be changed. Now you'll notice before we move on to other parts of the code that there's yet another variable type here, and it's called double. Now, up to now, we've been able to do all of our work using integers, that is, numbers that have no fractional or decimal part. But now we're going to want to actually be able to work with decimal numbers. And a good way to do that is to use scientific notation or exponential notation. That is, to be able to represent a number as some fractional part times 10 to some power. So for example, 30,000 could also be written as 3 times 10 to the 4th power. Now, numbers like that can also be represented in binary and can go to much greater ranges than is possible, say, with an int or an unsigned int. And so one of those types of variables is called a float. Float is just short for floating point number that implies that it has a decimal point that can be anywhere. A float variable is capable of going all the way up to plus and minus about 10 to the 38th power, which is a pretty big number. We could probably work just fine with that in the present example. If you needed more range, you could use an even longer floating point number called a double. A double just has twice as many bits as a float does, and double is just short for double precision. So a double precision, or just for short, a double, can go all the way up to 10 to the 308th power. So that's a huge number, more than we'll ever need. And so we're going to go ahead and use double precision for our non-integer number here. In this case, we're going to use the double precision variable %full to basically calculate how close our battery is to full. So if it says 54.3%, that will tell us how close we are to having a full charge on our batteries. All right, so that's a little review of variable types other than integers. The next thing that we want to introduce ourselves to is the idea that we're not restricted to only having the setup and the loop routines in our code. We can actually define our own functions and use those, say, in loop. How would that work? Well, what I'm going to do is I'm going to keep our original setup, and you'll recognize what setup did from our last session. In this case, setup just did two important things. It set pin mode for our onboard LED to an output so that we could flash it on and off when we wanted to. and it started up the serial monitor. So that will not be changed, and we'll keep that the same. What we're going to do now is we're going to introduce a new function, and we will just put that in here after setup. That's a convenient place for us to put it. So let's go ahead and put this new function in, and let's have a look at what it does. I'm going to put a little space here so that it doesn't look like it's part of setup. All right, you'll notice that this new function has a name, and its name is print battery percentage. Void is just a way of telling us that this function does not actually return a numerical value, it just does something. Print battery percentage does what's inside these curly brackets between here and here. So let's just read through it and look at the comments and see what it does. The first thing that print battery percentage does is it prints the value of ticks, which you'll remember is just whatever the time is that's elapsed so far. And you'll wonder, well, how does ticks get changed? That will be discussed shortly. Next, we print to the serial monitor a little caption that says milliseconds, then puts some space in, and it says charge at space. Now, what's going to come after that? Well, what's going to come after that will depend upon how much charge has actually accumulated. So what we're going to do is when we wait for a certain amount of time, current times time is equal to charge. So if we wait for a fixed amount of time, then that multiplied by our measured battery value will basically tell us how close we are to battery capacity. So let's take battery level, divide it rather by battery capacity, and then multiply that by 100. That will be the percentage that battery level is of battery capacity. Multiply it by 100 and it becomes a percentage. Now, let's print out the percentage, and that will just come out after charge at. So it will tell us what the percentage is. And finally, print with print ln, which will basically end the line and return the percent symbol. Okay, so we're going to do that repeatedly. So we make that into a function that we can call whenever we need to do it. All right, that's pretty good. And now we have to focus our attention on what's happening in loop. So quite a bit is going to change here in loop. As I mentioned, we're going to de-emphasize for the moment the flashing LED function and focus more on what kinds of information that we need to get from our circuit, through the analog pin function, and what actions that we take in response to that. So we're going to replace this loop function now with a new loop function that's a little bit complicated. So we will take our time in stepping through it and trying to understand just what it does. So let's go ahead and put that in and have a look at it. All right, so as we start loop, the first thing that we do is we do something that should be familiar to you from our last session. We measure using analog read the value of the voltage at our sensor pin. Now, we assign that to the variable sensor value, which you'll remember is an integer. It's going to be some integer value between 0 and 1023. And rather than just taking that value and doing nothing with it, what we're going to do is we're going to add it to the previous value of battery level. And that uses a new construction that we're seeing right here. Battery level plus equals sensor value. That's just shorthand for take battery level, add sensor value to it, and put it back in battery level. That's what this statement does. So you can think of every time an execution of loop occurs, battery level will have added to it however much the current sensor value is. So it'll just constantly be going up and up and up. And the rate at which it goes up will depend upon how bright the light is that's falling on our photoresistor. So we should see battery level rising rapidly when the light is bright. We should see it rising very slowly or not at all when the photoresistor is dark. So we'll be looking out for that when we test our code. All right, so once we've done that, we're also going to say, okay, the time has just gone ahead by 1 wait time. So let's take ticks and add wait to it and put it back in ticks. So that's what's meant by ticks plus equals wait. So battery level's been updated. The time has been updated. And so now let's go ahead and do a test, a logical test. If battery level is greater than or equal to battery capacity, which another way of putting that is if battery level is greater than or equal to capacity, we've reached 100%. And so what we're going to do is print out ticks, the current time, milliseconds, and fully charged. So that will be printed out instead of the normal thing that will be printed out if we haven't reached 100%. So if we haven't reached 100%, then nothing will happen inside these curly brackets after the if. Instead, what will happen is what's after the else. And what's after the else is print battery percentage, our function, our custom function, which you'll recall, if we go back up here and look at, simply reports the current time and the current percentage of charge. So there's two possibilities. One is that we'll just simply print the current time and percentage, or the other is that we'll declare it fully charged and then just zero out the time and put in a really long delay so that it will just sit there for a long time and say fully charged. So that is almost finished. You'll remember that, of course, once we reach the end of loop, we just go back up and start again. We don't want to immediately start up again because we want to wait for our specified period of time, which in this case was 100 milliseconds. So we put in a delay of wait, and then off it goes to make the next loop. All right. Hopefully, that's a fairly clear explanation of what our new code is going to do. So we're just about ready to give it a test. This is some fairly extensive modifications that we've made here. So let's just check it and see if it compiles. So we'll click the verify button. And we made a mistake. We've got a problem. It says it's expecting a semicolon before this curly bracket. Sure enough, I forgot to end this delay statement with a semicolon. So I add that semicolon, save the change, and now let's verify it once again. Compiling. It worked this time. So I caught an error there before I caused problems for me. All right. So once we're fairly confident that we've got the code correctly entered, let's go ahead and start up the serial monitor so that we'll be able to see just what's coming out of the hero once we begin operation. I've got my flashlight handy so that I can check to see what happens when I increase and decrease the light illumination on the photoresistor. So let's go ahead and upload the code. Take a couple of seconds here to finish uploading. And once it does, we should be able to, okay, it's done uploading. And we now have updating information. you can see right now that the charge is slowly rising, 7%, 8%, 9%. What happens if I shine the photoresistor on it? Oh, now it's going up much more quickly. If I take the flashlight away, it goes back down to a slow rate of rise. Flashlight back, now it's charging rapidly again. We're all the way up to 50%, 60% almost. There we go. Back down, if I cover it up, if I were to cover up the photoresistor, I should see it rising almost not at all. Okay, and so let's go ahead and uncover it, and let's let it finish. We're up to 75%. Let's see if our logic successfully works to stop it. 97, 99, fully charged. So we have succeeded in achieving what we wanted to achieve. That is, we've controlled the output of information telling us what the state of charge of our batteries are. And with some added logic, we could do additional operations. We could presumably control analog or digital pins on our Hero that might be used to turn on or turn off certain circuits. So hopefully you can see how useful this is going to be to us. We are now really making great progress. We're learning new techniques, both in terms of the processing of data and in being able to make logical decisions so that the Hero can automate processes for us. So with that, we will stand down for today's session. You can go ahead and practice this and perhaps customize the code on your own to perform similar or different functions. And until next time, remember that we want to build everything and invent safe.